So here I'd just like to make some comments and define even and odd functions. Definition: an even function satisfies f of negative f equals f of x. An even function satisfies f of negative x equals f of x. An odd function satisfies f of negative x equals negative f of x. These definitions, these properties, have nice visuals on the Cartesian plane. They're given in this remark. An even function is symmetric about the y-axis, and an odd function is symmetric about the origin. Now, why is that? Why does this property tell us that? Well, why do these properties tell us those? Well, let's look at them. An even function, for even. This will be an informal answer, I guess you could say. Even function, f of x evaluates to that y value. For an even function, f of x, let's say it evaluates to that y value. What does negative x do? Well, negative x is over there. F of negative x is the same as f of x. So it also goes up here. So anything that exists on that side of the y-axis is going to exist on this side of the y-axis. So if you have a point like this, that's going to be over here as well. If it goes through 0, it goes through 0. So an even function could look like that. Absolute value is an even function. And why does that work for odd functions? Well, let's look at that. For odd, I guess this is a continuation of that example. For odd functions, symmetric about the origin. Well, here's x. Let's say f of x is somewhere up here. Well, what does an odd function satisfy? It satisfies this second property. This property down here. F of negative x, so here's negative x, equals the negative of that y value. Well, this y value is that much. The negative of that y value is that much going down. So anything that exists up here is going to exist down here in the third quadrant, like that. So if we have that there, that would be there, and similarly it could go through the origin. And an odd function would be symmetric about the origin, like that. So what are some examples? Well, in this informal proof of that remark, you may have come up with a couple examples. Example: f of x equals x squared. We'll do even functions first. And f of x equals cosine x. And absolute value of x. But I'm not going to write that here. Yeah, maybe I will. And f of x equals absolute value of x are even functions. How about odd functions? Well, f of x equals x cubed, and f of x equals sine x are odd functions. Now, why are they called even and odd? And do they have anything to do with even and odd numbers? Well, you may look at the first of each of those, the first example in each of those, and notice 2 is an even number and 3 is an odd number. Well, unfortunately, in Calc 1, I can't say more about that for cosine and sine. A similar phenomenon exists in the power series expansion for cosine and sine. What's a power series expansion? Well, last month of Calc 2. But why am I introducing even and odd functions right now in the middle of, well, at the end of the fundamental theorem of calculus? Well, we have two nice theorems for even and odd functions based on those symmetry remarks. If f is even, then integral from negative a to a of f of x equals something. And part 2, if f of x is odd, then integral from negative a to a of f of x with respect to x equals what? Well, before I give you the answer, maybe you should try to figure it out just with a drawing of a function symmetric about the origin. For the second one, symmetric about the y-axis for the first one. Well, what do we get for an even function? Let's take x squared. There's x squared. Nah, I don't want to take x squared. Yeah, I'll take x squared. Probably should have done cosine. Yeah, whatever. There's a. There's negative a. The integral measures from negative a to a, takes this area and adds it to this area. But this is symmetric about the y-axis. So this area equals this area. So if we want those two areas combined, well, we can just take this area over here, which is given by, let me write it a little better than that, which is given by that definite integral from 0 to a, and then take two of them. For cosine of x, what would that look like? Well, this area over here, if you just restricted yourself to these first two pieces, well, to this first lump of cosine, that area equals that area over there. And how about for an odd function? What would that look like? What would the integral from negative a to a of an odd function look like? Well, f odd. Let's do sine. There's sine, and so on. Let's just say a happens to be, what is that, pi? A and negative a. The area here, from negative a to 0, the area is the same as this area. Just as area quantities, those are the same. But the definite integral treats this area as a positive, I'll just call it capital A for area, and it treats this area, which is also capital A, as a negative. If f is odd, this area and this area are going to be the same, but the definite integral says, well, the definite integral evaluates to what's above the x-axis minus what's below the x-axis. A minus a is 0. So we have two nice visuals for these functions. And I like these two results. And on every final, I don't ask to prove these results. I don't ask to state these results. I don't mention even or odd functions anywhere on the final. And I won't. But these observations do make some computations a little easier. And on every final, there is a computation which you can do without this observation, but which is easier with one of these observations. I haven't written the final yet, but there definitely will be something where an even or odd observation is relevant.